So the question is, how did we obtain that particular number? And what's happening in this particular process? So the half reaction occurring at the anode is our oxidation half cell. So in the oxidation half cell, we have copper solid that's being oxidized to copper 2 plus in aqueous solution plus 2 electrons. We need to know the standard potential for this particular reaction. We know what the reduction potential is for copper, but in this case, we have an oxidation half reaction. If we have an oxidation half reaction, it's just like saying we're flipping the sign. So this cell potential is going to be negative 0.34 volts. If we have a cathode half reaction, which is the reduction, the species being reduced is the silver plus ions in aqueous solution plus an electron, giving us silver solid. The cell potential for this particular reaction is actually the reduction potential, which is positive 0.80 volts. One of the things that we observed when we put this stuff together was that our overall cell potential, which was experimentally determined, was positive 0.46 volts, which is going to be the sum of each of these cell potentials. Now the question is, how do we get to this overall reaction? We have to make sure that all the electrons here cancel out. In order to cancel out the electrons, we need to multiply the cathode half reaction by 2. So I need a 2 in front of the silver, a 2 in front of this electron, and a 2 in front of the silver solid. One thing to note, that when we look at the properties of these electrochemical reactions, the cell potential is an intensive property. That means it doesn't matter on the amount. So our cathode metal could be large, it could be small. That value is not going to change. Okay? So when we write out the overall reaction, we need to make sure that we balance so we can cancel out our electrons, but we are not allowed to touch that cell potential value. So the overall half reaction that we have is copper solid plus 2 silver ions in solution, giving us copper 2 plus ions in solution plus 2 silver solid. This gives us the experimentally determined voltage, which was 0.46 volts. And that's going to be the sum of each of these two potentials. Okay? It depends on how you look at this in terms of the signs and everything. I find it a lot easier to look at the oxidation reaction, which you flip the sign from the reduction potential, and then add that to your second reaction, which is your reduction reaction, which will be the value you'd find in the table, and then just add those two together. So this is going to clarify or show that this value right here that we theoretically determined is going to equal what we experimentally determined. There's a couple things that I want to mention about these particular reactions. Okay? So things that are very important that we need to note. Number one is when a half reaction is reversed, the sign is also reversed. Or I should say, the sign is also reversed for our potential, or our standard potential. Another thing to note is that our cell potential, or our E naught, is an intensive property. What an intensive property tells us is that it does not depend on the amount of the substance present. When we set these things up, I didn't emphasize this much yet, but we certainly will do so from here on forward. If you have a galvanic/voltaic cell, it must occur spontaneously. And depending on the way we look at this, in this case, why does the copper have to be the anode and the silver have to be the cathode? The reason for that is because it needs to be a spontaneous process. So if we look and compare spontaneity, which we will a little later on with calculations, but for now, we're going to say to run spontaneously, the overall cell potential must be positive. So when we looked at the Gibbs free energy, if something is spontaneous, delta G naught is negative. The reverse is true for the cell potential. If E naught is positive, then our reaction is spontaneous. So we can look at this particular reaction, and one thing that we can do, a lot of times, rather than draw all this stuff out, we need to come up with kind of a shorthand notation of the simplest way to draw this stuff. And that shorthand notation for this particular reaction that we have drawn here at the bottom of the page is going to be, if you have copper solid, and we put a straight line down here like this, and then put copper 2 plus as an aqueous solution, then we draw two straight lines up and down like this, and then write silver plus in aqueous solution, one more straight line, then silver solid. This is the abbreviation for this entire process that we just described right here. And what this is going to tell us, on the left-hand side of this notation, we have the anode. So our copper is being oxidized to copper 2 plus. And on the right-hand side, we have the cathode. So you should be able to go from this notation to everything we talked about up here, or be given all of these schematics and then write this down in the shorthand notation. Notice that when we write the species on the left-hand side, the copper solid is being oxidized to copper 2 plus, so we put the copper solid on the left to right. And then for the cathode, the silver plus is being reduced to silver solid, so we also write those from left to right in our particular process. So this is the convention. If you see this abbreviation term down here, that's describing this entire process that we just analyzed. Okay? Let's go over another example of this. And in this particular example, we're going to bring out one other bullet point that we didn't discuss earlier. And that is that a chemically inert conductor is required if none of the substances participating in the half reaction are conducting solids. And when this is useful is we can set up these electrodes, and it's easy to set them up with solid metals and ions in solution. But we can have oxidation reduction reactions occur between gases. We can have oxidation reduction reactions happen between just ions in solution.